So yeah, I'm Tim Street. I am the Secretary of British Pugwash. Hello everyone, thanks for coming. It's the British Pugwash Annual Lecture. So yeah, just some housekeeping rules. Please stay muted during the talk. There'll be a Q&A, lots of time for Q&A after the talk. You can raise your hand or you post questions in the chat to raise your hand. If you look at the bottom of your screen, you'll see a react button. If you click on that, you can see a little raise hand symbol. So that's how you do that. I'm also managing the waiting room. So bear with me while I do that. So yes, David Ellwood is going to be our lecturer today, and he's going to be speaking on is even a minimal nuclear deterrent mad? So David is a theoretical physicist and mathematician who served for more than a decade as research director of the Clay Mathematics Institute. He's a member of the he's a member of the Pugwash Council and the executive committees of International Pugwash and the British Pugwash Group. So David's held academic appointments at Harvard, Boston University, Université de Strasbourg, ETH Zurich, Université de Paris 6, and the Institut de Haute Étude Scientifique. I hope I've said that right for anyone here from France. So yes, we're looking forward to hearing from David. Very lucky to have him here today. And please consider joining British Pugwash if you're not already a member. I'll put a link in the chat and you can see our website. But without further ado, over to you, David.
Okay, well, thank you, Tim, for that very kind introduction. And thank you to Peter, who invited me to give this year's lecture. I'm extremely grateful. And thank you both for all the work you do. British Pugwash has a really amazing YouTube channel. So if this is the first time you've tuned in for one of these talks, then I recommend that you consult the YouTube channel because there's some really excellent material on there. So thanks for those who have stayed and for those joining the discussion this evening. I've chosen to talk about the climate effects of nuclear war because I think it's an important area of research through which science can help advance policy. After all, that's the raison d'etre of the Pugwash movement. To do this effectively, I firmly believe you need to understand both what the experts are saying and also how they came to say it. So this talk will be about understanding. I hope it will empower you to ask the sorts of questions that will advance both science and the policy agenda. Science is currently really under threat in some very unexpected places in the world at the moment. So it's very important that we try to support science at this time and speak up for science. An important thing about science is it doesn't depend on authority. The key is always to convince yourself of the relevant conclusions. If you can do that through a process of your own deduction, then you can talk to others legitimately and maybe find the power within yourself to help bring some small change to this world. Okay, so let me see how I can change slides. Just trying to find the controls here. Okay. So as you heard, I'm a theoretical physicist. I'm not a climate scientist, so I'm not reporting my own work this evening. Here's a list of the references I've consulted. Besides the ones that are frequently cited, I would like to draw attention to the excellent talk by my colleague on the Pugwash Council, Venance Journet, who kindly shared her slides from Castiglioncello with me. And also a very insightful paper by Philip Weber I've highlighted here. He co-chairs the UK-based Scientists for Global Responsibility. Note that the subject began in the early 80s with a paper by John Birks and chemistry Nobel laureate Paul Crutzen. I'm afraid the advance is not working at the moment. Ah, there we go. There we can see Paul. Crutzen won the Nobel Prize for his work on atmospheric chemistry, specifically the understanding the formation and decomposition of atmospheric ozone. Still struggling with this. He's also well known for arguing that we've entered a new geological age called the Anthropocene, which is recently not accepted by the International Geophysical Union, but nevertheless, it's the age in which human activity has become a planetary force. It's still a very popular term, and one I think that's very important. I should mention he also introduced the concept of geoengineering or climate engineering, fearing more than 20 years ago that our societal response to global climate change would be so pathetic that we might have to interfere with the Earth's albedo to control our climate response. Incidentally, Curson also debunked the idea that biofuels could save us. He showed that the nitrous oxide emissions in the mass production of biofuels will contribute more to global warming than the fossil fuels they were set to replace. The other gentleman here I'm really struggling with this system here. The other gentleman here is, of course, Carl Sagan, a planetary scientist and astrobiologist, but someone who also had a large, very successful career as a science communicator. He helped spread the understanding and the public appreciation of science in his famous paper with Turco and Toon, Adamek and Polak really helped spread the message about nuclear winter, and he had a genuine impact on climate policy. So let's see if we can get this moving. So where are we in all this? I hope some members of the general public have joined us tonight. So it's important to restate really where we're at. In the middle of the 20th century, after 300 years of breathtaking progress in physics, we've culminated in what? A dystopian age in which a few men can destroy civilization within a few minutes of deciding to do so. It's a really incredible situation. Of course, these two men in particular, Trump and Putin, but also Macron, Starmer, Modi, and Netanyahu can kill hundreds of millions within hours. During his impeachment proceedings, Richard Nixon boasted, "I can go into my office and within 20 minutes, I can kill 70 million people." We now know that Nixon had vastly understated the power at his disposal, and not just his, but the force wielded by each of his successors, and presently by every one of these gentlemen before you. Let me be clear that what we are discussing here is not merely a hypothetical situation. Nixon, as well as Eisenhower, Kennedy, and Johnson, each contemplated using nuclear weapons. Eisenhower twice, Kennedy 3 times, Johnson once, and Nixon 4 times. The future of the human race truly hangs on the character and judgment of how these 8 men react under pressure in the fog of war. This is a terrifying status quo, and we've created it. It's so bizarre it's hard to grasp, and since the end of the Cold War, it's off the radar of the general public. Tragically, not because the threat has diminished, the danger is as extreme as ever, unstable, and getting worse. The gravest danger comes from not the risk of accidents, acquisition by terrorists, or rogue countries, but from the mistaken idea that there exists some case for the possession of these weapons compatible with legitimate governance. There isn't. As Mikhail Gorbachev, a good friend of Pugwash, once said, models made by Russian and American scientists showed that nuclear war would result in a nuclear winter that would be extremely destructive to all life on Earth. The knowledge of that was a great stimulus to us, to people of honor and morality, to act in that situation. So why are we here? Why have we created this situation? Well, it's this interplay between the concept of deterrence and diplomacy. Deterrence and diplomacy are supposed to work alongside one another, but do we have the balance right? Should they be given equal weight, or is the correct balance dynamic, i.e. continuously adjusting to present circumstances? Roughly speaking, we're talking about the stick and carrot approach to international relations. Does a big stick really confer greater security? That depends on who feels threatened by it, and more importantly, how they might react to that threat. Even if you believe in big sticks, the pertinent question is, how big is big enough? And as soon as we adopt such an approach, how can we avoid falling into an endless cycle of military buildup, a race to build ever larger and more lethal sticks? In this talk, I will focus on the first problem, but I would like to remind you that the latter can only be solved through diplomacy. Multilateral institutions can do much to temper the militaristic zeal of individual nation states, but at its heart, diplomacy is a form of interaction, and to be effective, we must all agree to rules that optimize the chances of achieving outcomes preferable to another arms race. In this regard, I'm sad to say that we currently find ourselves in a very dismal state. Diplomats often don't speak to one another, and the rules of the game are neither obeyed nor optimized to steer nations towards greater harmony in international relations. If we are to lessen the risk of catastrophic conflict, we should support our multilateral institutions with renewed vigor. We must reject the practice of diplomacy as a game of chess in which the nations are checkmated, and instead embrace the Pugwash model of dialogues across divides. Ultimately, for international law to become effective, nation states must agree to pool their sovereignty on certain issues regarding international security. So if we accept the concept of a nuclear deterrent, there are many questions that must be answered. How should a nuclear deterrent meld with that provided by conventional forces? How big is big enough? And big enough for what? In particular, the answers must address what sort of attack we intend to deter and by whom. Even defining what we mean by nuclear deterrence poses severe problems, because the better we understand the nature of nuclear weapons, the harder it is to cast them in a rational light. Moreover, history suggests that even the biggest sticks often fail to confer the security guarantees nations seek. One thing is for sure, nuclear weapons introduce a striking asymmetry into international relations, one that favors aggression and inequality rather than greater cooperation and peace. This asymmetry and the absence of a common security architecture for the global community makes it more likely that states will seek the protection of a nuclear deterrent in the future. That both Sweden and Finland have recently joined a nuclear alliance is very revealing. Finland's conventional armed forces are extremely capable, but a Finnish analyst recently told me that the reason his country sought a NATO membership was its nuclear umbrella. So if a modern, well-equipped conventional forces are not considered a sufficient deterrent, what capability must one add to address the latent insecurity that remains? To know what is just right in such a hypothetical situation, it's necessary to explore the limits of what is too big and what is too small in the world of weapons of mass destruction. So let's begin by asking, what is too big? Well, the dinosaurs knew the answer to that. In 1981, the physicist and Nobel laureate Luis Alvarez, together with his son Walter, suggested that the Cretaceous-Paleogene extinction was caused by a massive asteroid hurtling into the Gulf of Mexico. It is estimated that 75% or more of all species on Earth vanished in a geological instant. In the geological record, the KPG extinction event is marked by a thin layer of sediment called the Fatico boundary, which can be found throughout the world in both marine and terrestrial rocks. The Alvarez's noticed that this boundary clay exhibited unusually high levels of iridium, which is more common in asteroids than in the Earth's crust. In the 1990s, a massive crater under the Yucatan Peninsula called Chicxulub, named after a nearby village, was identified as the site of the impact. Analysis of core samples from the crater provided strong evidence that the KPG boundary clay represents debris from an asteroid impact, and recent supercomputer simulations have revealed the details of the impact in extraordinary detail. On an otherwise ordinary day in the late Mesozoic, a massive asteroid, approximately 17 kilometers in diameter, approached Earth from the northeast at an angle of 60 degrees from the horizontal. Simulations suggest the asteroid has a density of approximately 2,630 kilograms per cubic meter and plowed into the Gulf of Mexico at about 12 kilometers a second. The impact created widespread tsunamis, sent a seismic shockwave around the planet, and left an impact crater 300 kilometers wide and 3 kilometers deep. A fast-moving dust cloud encircled the Earth, and within a few hours, the climate-active gases from molten rock rich in sulfur, together with vast amounts of black carbon from the burning hellscape, were injected into the atmosphere. Sulfuric acid aerosols quickly adhered to heavy silica ejectors and induced acid rainstorms on a continental scale, causing episodic acidification of both the terrestrial and aquatic ecosystems. So let us return to the question of deterrence and compute the TNT equivalent yield of the Chicxulub impact. From the computer simulations, we can estimate that the energy carried by the asteroid, the kinetic energy, was 72,000 joules per gram. That's an astonishing amount of energy. An asteroid approaching at this speed has an explosive yield about 18 times that of TNT. We can use the figures from these supercomputer simulations to also estimate the total energy carried by the asteroid, and it works out at about 122 million megatons. Again, a fantastic amount of energy, and one we should say that gives us some comfort in designing a nuclear deterrent that won't destroy the planet. The largest nuclear weapon ever tested was the Tsar bomb, and that had a yield of 59 megatons. And the cumulative US strategic arsenal megatonnage is about 820. So the yield of the Chicxulub impact was about 150 times the size of the US strategic arsenal. So it would seem we had plenty of headroom to play with, but not so fast. A nuclear deterrent is not a single massive weapon, but an arsenal of much smaller weapons whose energy may be applied over a wide area to maximize the net damage efficiency. Nuclear war planners are mainly concerned with blast effects, so they think in terms of blast effects or targets, which are necessary localized entities. If you consider an air blast of 125 kiloton weapon, the 5 psi overpressure contour extends about 2.8 kilometers from the hypercenter. That means pretty much all buildings and life, people will die within that 5 psi contour, which is about 25 square kilometers. There's a kind of rule of thumb. Of course, not everybody dies inside the contour, but some people die outside the contour. And, studies have shown that roughly these things balance out. So that's the kind of rule of thumb with which people work. If we scale up and consider the area of a 5 psi enclosed within a 5 psi overpressure contour for a 1 megaton weapon, we get about 100 square kilometers. Now, we don't need to deliver that as one weapon. We might use instead 125 kiloton weapons. So the yield is the same, but the area affected is double. So nuclear war planners have not adopted smaller weapons for any humanitarian reason. You get double the area for the same yield. It's a very alarming situation. Of course, the issue with multiple independently targeted reentry vehicles, which are on the current warheads in our nuclear arsenals, have an even worse effect than this. For a 90 kiloton weapon, you affect about 240 square kilometers with overpressure of more than 5 psi. But it wasn't blast effects that killed the dinosaurs. Even a blast the size of Chicxulub magnitude doesn't cause a mass extinction event. So what did kill the dinosaurs? Impact winter. The blast effect from the impact was like a mosquito hitting your windscreen. Its effect on the car is negligible, but it leaves a big mess on the windscreen. And for us, that means the Earth's atmosphere. 3D simulations on a supercomputer showed that a fast-moving dust cloud soon covered the planet. Thermal radiation ignites wildfires, which ejected more soot and black carbon into the atmosphere. Forests, land, and ocean plants died, unable to photosynthesize. "75% of all life on Earth either froze or starved to death." The KPG extinction event was severe, global, rapid, and selective, eliminating a vast number of species, and it appears to have affected all continents at the same time. The key mechanism to understand here is that of a firestorm. This is incidentally collateral damage for the war planners. This is not what they count on when they design the targeting for their nuclear war plans. But a firestorm is a weather system that is actually created by very large fires and takes over the local climate at that point. So as massive fires spread out around ground zero, superheated air rises up and forms hurricane force winds. This pulls in more fresh, oxygen-rich air that fuels the fire further, and it forms vast columns of smoke towers which tower into the sky and really up to the tropopause, the top of where weather really takes place, up to the level of the stratosphere, about 12 miles up at the equator. The soot that's carried up by this is self-lofting due to solar heating. So it continues to rise up in the stratosphere. And new modeling, as well as some experiments that have been done recently, verify that the soot rises to much higher altitudes than expected and is likely to remain 5 times longer than suggested by early 1980s modeling. This, incidentally, is the picture of Hiroshima after the nuclear attack. And it's often mistaken for the mushroom cloud from the bomb that was dropped on Hiroshima. Actually, it's the firestorm. Mushroom cloud would not be nearly so large. You don't need an asteroid impact like Chicxulub, of course, to generate a firestorm. Just the right conditions and sufficient quantities of thermal energy and combustible materials. Nuclear explosions, wildfires, and bombing raids can all ignite firestorms, but only if the conditions are right. London and Coventry were firebombed during World War II, but the raids did not result in a firestorm because they were not sufficiently concentrated in both space and time. British war planners understood this, and the raids on Hamburg and Dresden resulted in firestorms of 12 and 21 square kilometers, respectively. This was the goal in World War II, but it's just collateral damage for nuclear war planners today. As the historian Margaret Macmillan remarked, it was no oversight that mass bombings were not included in the Allied indictment of Nazi leaders at the Nuremberg trials. Nuclear weapons essentially reduced the question of whether a city will firestorm to a few predictable variables: topography, fuel loading, and the prevailing atmospheric conditions, particular wind speed. The 15-kiloton bomb dropped on Hiroshima on the 6th of August 1945 generated a firestorm, incinerating 13 square kilometers, but the 21-kiloton bomb on Nagasaki didn't. The difference was topography. Hiroshima is relatively flat, while Nagasaki has an uneven topography. So deaths at Hiroshima were caused by prompt radiation, blast, and fire. But these effects, bombs, radiation, and blast, the effects decline more rapidly with distance than does the thermal radiation and the fire effect. So if we calibrate on data from Hiroshima for a yield of 15 kilotons, we see 13 square kilometers burnt, and we assume linear scaling for small yield weapons, and we get, let's see if I can move this a second, about 86 and a half square kilometers fire zone for a 100 kiloton yield weapon. That's a radius of over 5 kilometers. That's basically everything you can see out to the horizon. So in general, city fire damage is less dependent on the yield of the weapons used than on conditions in and around the city. Fuel loading per square meter, or fuel density, is arguably the most significant factor. Data suggests the amount of fuel per unit area of an urban developed landscape is a linear function of population density. And we know we have very good databases for population density. For instance, a Landscan database maintained by the Oak Ridge National Laboratory gives daily average population in grid cells of about 30 by 30 arc seconds. That's down to a resolution about 1 square kilometer. So very good databases. The total single detonation mass of soot emitted by fires, adjusted for rainout, is given by this formula by the researchers which are currently working on these things. It's just a linear formula. I'll break it down for you. You sum over the region subjected by fire. You divide it into J grid cells. AJ is the area of the jth grid cell affected by fire, and MFJ is the fuel per unit area in the jth grid cell, estimated from the previous formula from the population database. The second term is just a constant term to adjust. It sums over different types of combustible materials, the fractions involved of each material, how much of that material is likely to burn following a nuclear ignition, how much of that material will be converted into soot, the ratio of of the types of fuel in relative to relative to a city in the developed world to the developing world. And Ri is a factor which adjusts for rain out, so the black rain that comes down in the firestorm. So researchers submit some fair assumptions into this formula. They do the algebra, and they come up with this equation to estimate the total syngonation mass of soot from fires after a nuclear explosion. So now, to understand the climate effects of a nuclear war, we must consider targeting. Defense theory favors a counter-value strategy in which urban areas are the most important, in which urban areas are targeted, and the most important civilian assets, rather than opposing nuclear forces. Thus, the areas of highest population densities are indeed in the crosshairs of nuclear war planners, and we can expect such a conflict to result in the production of the maximum amount of soot suggested by the formula above. Civilian studies don't have access to actual targeting maps of nuclear war planners, so recent studies have adopted a simplistic cookie-cutter approach to targeting, where warheads are directed at targets of highest population density in a non-overlapping grid so as to avoid any redundancy. This is certainly contrary to actual war plans, and it's an uncertainty in current modeling of nuclear winter, which is important to point out. The study should be redone with more accurate targeting plans, but the effects are likely to be of the same order of magnitude. If we look at a full-scale nuclear war between Russia and the United States, using these formulas, researchers have estimated a soot emission of about 150 million tons of soot. That's a lot of soot. This then gets input into modern climate models, or global circulation models, as they're called. Now, these are very sophisticated simulations of the Earth system, and they're done on a supercomputer. Now, computers, despite all the hype around AI, ultimately all the computer can do is arithmetic. So when you're doing when you're modeling in this manner, you have to divide whatever you're modeling up into grid cells and estimate the parameters for each grid cell and then let the model get to work. The models for climate change approximate how much energy and matter, how energy and matter interacts in the ocean, land, and atmosphere. They compute the movement of energy and water and gases and aerosols, etc., into and out of this 3D array of grid cells. Now, we understand the laws of physics involved in the dynamics very, very well. So it gives you a sort of confident feeling that one should be able to make accurate predictions. The thermodynamics and conservation of mass and energy are all physics that we really understand well. But remember, we understand the laws. It doesn't mean we can perform the computations, which are fantastically difficult. And as you know, for instance, when you know from looking at your daily weather forecasts, it's very difficult to predict the weather 2 weeks out. But the goal of these models is not to predict weather, it's to predict climate. And so they want to average the behavior over much longer time periods. The problem is, needless to say, very difficult. Now, when I say very difficult, I mean extremely difficult. I mean, as a theoretical physicist, we look at the very first few fractions of a second of the early universe, which we can understand in quite some detail. But the complexity of the Earth system is the most complex system we know. It includes us. And so modeling it is extremely complicated. And the equations involved are extremely complicated to solve. For instance, the Navier-Stokes equation, which governs fluid flow. The institute, which I used to work for, offered $1 million if you could just prove the existence of smooth solutions to the Navier-Stokes equation. So let alone solving them, just proving that solutions actually exist to these equations is very complicated. So doing numerical modeling is a big task with many, many uncertainties involved. There's also a big trade-off between the higher the resolution that you look at, the temporal and spatial resolution, and the computing power you need to do that. So if you try to make the models more accurate, you need more computer time to affect that, even on the largest supercomputers in the world. Observations, our current observations, the data that we can put into these models of the ocean atmosphere is really not adequate at the moment. We just don't have that much information about our planet. So the atmosphere is split up into millions of cells, and the ocean hundreds of millions of cells. We just don't know what parameters to specify in such a large complex model of the Earth. The approximations also have to make subgrid assumptions, they're called. It's necessary for the small scale features, which for these models are clouds. Even in the most sophisticated models, we're looking at these grid cells are about 100 square kilometers and tallying up to 20 layers over the Earth. So it's a rather crude approximation, nevertheless. In the ocean, climate scientists use smaller grid cells of about 10 by 10 kilometers and up to 30 layers deep. There's also a trade-off between how fine you can make the grid cells and the time step involved. You don't want effects in one grid cell to be able to propagate further than its nearest neighbor within the time step. So sometimes you have to reduce the time step if you increase the accuracy and the resolution of the model. Finally, there's fine tuning, but needless to say, in such a complicated model, there's nothing fine about it. So climate scientists work very hard to try to tune these models so that the predictions they give are more realistic. But some of the assumptions they make are very of much concern. I mean, very unphysical parameters are put into the models to try to get them to fit. Now, the problem of modeling nuclear winter is a somewhat easier problem than modeling global climate over the next decades and centuries. So you have one large event that you seek to model. And here you can see a simulation that was done by Robock and his collaborators in 2007 with 23 layers of atmosphere and 13 layers of ocean and a 4 by 5 degree grid cells. This model was calibrated using satellite observations of volcanic eruptions, forest fires, and the Gulf War. And it's quite striking to see how quickly the soot rises up into the upper atmosphere and then spreads around the globe. So here you see the optical depth, which is basically a measure of how opaque the atmosphere is to sunlight. And you can see it's over a period of weeks, and within a month, you get the whole planet covered in an enormous cloud of soot. The soot is self-lofting, as I mentioned, due to solar heating. It rises into the stratosphere where it remains. During the first week, we saw the soot spread over the targeted countries, and the soot starts dispersing into the southern hemisphere in the second week. The optical depth is a measure of the transmitted to the incident radiation. It measures the ability of the atmosphere to block sunlight. The larger the optical depth, the smaller the amount of transmitted radiant power. An optical depth of 0.1 means 90% of incident radiation reaches the Earth's surface. So it's quite a shocking simulation. And I should say, for all the caution that I've mentioned about climate modeling, if you believe anything about climate science to date, then you should certainly believe these predictions, because these are much firmer ground than our predictions of the course of weather of our climate over the next 50 years. Again, this is what is considered collateral damage by our governments today, the phenomenon called nuclear winter. And if you're not really convinced by climate modeling, in any case, the way physicists work is we try to do back of the envelope calculations, because that gives us a feeling of how to write these models, how to adjust them, and how to make sense out of what we get out of them. So you can consider the radiative forcing, that's the change in energy flux. The energy that's coming into the Earth from sunlight and the energy that goes back is radiated back out by the Earth. So the difference between that, when the planet is not in equilibrium, will cause either global warming or global cooling. The maximum normal surface irradiance, that's the radiative power of sunlight received at the Earth's surface, is about 1,000 watts per square meter. With 150 teragram soot injection, that will reduce the radiative power, the radiative power of sunlight on the surface of the Earth by about 10%. Now, one of the basic laws of physics, the Stefan-Boltzmann laws, thermodynamics, is that implies that the percentage temperature reduction in degrees Kelvin is about a quarter of the watts per square meter reduction in radiant energy. So for a 10% reduction in radiant power, you get a temperature change of about 13.5 degrees Fahrenheit or 7.5 degrees Kelvin or Celsius. So it's a very, very marked climate event, like nothing we've seen in our history as a civilization. You have to go back to the last ice age to see anything like this. Of course, what my back of the envelope calculation doesn't take into account is feedback effects. The lower temperature results in more snow and ice and an increased albedo for the planet. That means the planet becomes more reflective of sunlight, so less energy gets absorbed. And also the lower temperature implies there's less atmospheric water vapor. And water vapor is, of course, the ultimate greenhouse gas. It's the most powerful greenhouse gas that's never mentioned. This results in crop failure, growing seasons are reduced, precipitation reductions, and ozone depletion. It's basically a catastrophic shock to the climate. Let's see. The same researchers looked at a regional nuclear war scenario, India versus Pakistan. And so for this, they estimated an exchange of about 100 Hiroshima-size nuclear weapons, which resulted in just 1.5 megaton yield. That generates sort of about 5 million tons, or 5 teratons. And you can look at the effect of this, again, in one of these simulations. You can watch it spreading out from India and Pakistan. And with a very short time, it's not only risen up to the stratosphere, but it's encircled the planet. We're looking at a 1,300 square kilometers fire zone generated by 5 teragrams of soot. And after rain out, the soot raises into the stratosphere, as I said, and there's reduced solar irradiance for years to follow. So you can then compute again to sort of convince yourself that this looks right. The radiative forcing, the change in energy flux. 5 teragram soot injection has reduced the energy flux by 16 watts per square meter. Stefan-Boltzmann law predicts a temperature change of about 1.2 degrees Celsius. That's a mini ice age in itself. The coldest temperatures we will have seen on Earth for about 1,000 years. A 20% reduction in ozone columns globally, and a reduced growing season and drought for at least 5 years. Agricultural ecosystems collapse, and that's just the response of the Earth. But the response of our civilization would be catastrophic, because you're going to see severe food shortages and starvation, and very, very dramatic effects. More people are estimated to die outside of the war zone than within the war zone. So let's turn now to the concept of a minimal deterrent. Because, we're not looking at a full-scale nuclear war, and maybe we can still gain some security by adopting what is considered to be the gold standard in minimal deterrence, which is what the UK has adopted. UK has been a nuclear weapon state since 1952 and is one of the 5 officially recognized nuclear states under the Non-Proliferation Treaty. Sorry, my laptop stops working from time to time. UK adopts a posture of minimal credible nuclear deterrence assigned to the defense of NATO. The UK does not have a policy of no first use. The UK also has a policy of deliberate ambiguity. That is, it does not make clear the precise details of when, how, and at what scale the UK may consider the use of its nuclear weapons. In the 2021 Integrated Review of Security, Defense and Development and Foreign Policy, and its subsequent refresh in March 23, confirmed that nuclear weapons would be only used in extreme circumstances of self-defense, and the UK will not use or threaten to use nuclear weapons against any non nuclear weapon state party to the NPT. Notice that. Notice the UK's position of deliberate ambiguity. The UK will no longer provide public figures on the UK's operational stockpile, deployed warheads, and deployed missile numbers. The government claims that this ambiguity complicates the calculations of potential aggressors, reduces the risk of deliberate nuclear use by those seeking a first strike advantage, and contributes to strategic stability. Now, this claim should be carefully weighed. An obvious concern is that such a policy is that it's the uncertainty it creates in the mind of others. So this gives me an opportunity to show a picture of my professor who introduced me to Pugwash many, many years ago. He was my cosmology professor at Imperial College. This is Tom Kibble. And in evidence submitted to the Trident Commission by Tom, Keith Barnum, David Kaplan, and Jenny Nelson, they wrote, "The Quinlan Doctrine justifying the UK nuclear weapons asserted that they created additional uncertainty in the mind of any potential superpower adversary. While this doctrine may have provided some intellectual comfort in the upper echelons of government, in our view it was extremely dangerous and therefore totally irresponsible. Within a conventional weapons scenario, it may well be that to create uncertainty in the mind of an adversary is tactically advantageous. With nuclear weapons, the response to uncertainty has to be assume the worst case, so that there is overriding pressure on the adversary's missile forces to use them or lose them." And I agree with Tom's thoughts on that entirely. So as one of the recognized nuclear weapons states signed up to the NPT, the UK has a legal obligation to pursue disarmament in good faith under Article 6 of that treaty. The UK has also signed the Comprehensive Test Ban Treaty in 1996 and ratified it in 1998. Although the treaty is yet to enter force, the UK abides by its commitments and has maintained a moratorium on nuclear testing. The UK also supports negotiation of a fissile material cutoff treaty, and the UK has not signed the treaty on the prohibition of nuclear weapons. The UK Integrated Review confirms that the long-term goal of a world without nuclear weapons, its long-term goal is that, and said that it's committed to the full implementation of NPT in all its aspects, including nuclear disarmament, non-proliferation, and the peaceful use of nuclear energy. However, the UK government's view is that the NPT is the only forum through which multilateral disarmament can be achieved, and that no credible alternative route to nuclear disarmament exists. Decisions about disarmament must take into account the prevailing security environment. So just to review the composition of this gold standard of minimal nuclear deterrence. And its Cold War peak, the UK's nuclear stockpile consisted of approximately 500 nuclear warheads. But following the Cold War, this was reduced. The dumb bombs were phased out. The capability of Royal Navy ships to deploy nuclear weapons was dismantled. And the system was reduced to a single submarine launch-based nuclear weapon system. The UK is the only nuclear weapon state that is reduced to a single deterrent system. That system consists of 4 Vanguard-class submarines, maintaining continuous at-sea deterrence, 58 Trident missiles, which are held in a communal pool with the US, situated at Kings Bay submarine base in Georgia, varying numbers of Mk4A nuclear warheads that can be deployed on the Trident 2D5 missiles. And in 1998, the UK government announced the deterrent patrol cycle was reduced to a single SSBN on patrol at any one time. The number of warheads carried on board deterrent patrol was reduced to 48 from a previous ceiling of 96. The missiles on board were de-targeted, while the notice to fire period was increased from a few minutes to a notice period measured in days. In 2010, the government published official information on the UK's overall nuclear stockpile for the first time, confirming that it held 225 warheads. Also, the number of operational launch tubes on Van-class submarines would be reduced from 12 to 8, and the maximum number of warheads deployed on board were reduced to 40. However, in 2021, integrated review on the cap of the UK's nuclear stockpile was raised to no more than 260 warheads. The review did not provide a time frame, nor did it state how many of those 260 warheads will be operationally available, in line with the policy of not disclosing such data. The UK retains the smallest inventory of any recognized nuclear weapon state. However, the UK and China are the only members of the P5 that are quantitatively increasing their nuclear stockpiles. So we're still left with this fact that a relatively small number of weapons are needed, only a relatively small number of weapons are needed to destroy cities and the economy of even the largest country. And to say what that means, the concept of a minimal deterrent, McNamara gave us some idea of what's in the minds of war planners, is to retain the capability of destroying about 25% of the population of your adversary and 50% of their industry. Now, this concept is problematic at best because security guarantees given by it are not credible. Whatever a minimal deterrent is, it's not a nuclear umbrella. And contrary to international humanitarian law, threats of the use of force must not be directed at civilians. Impacts are disproportionate and also affect areas including regions remote from the war zone. It's also delusional. It ignores the threat felt by others, which increases insecurity. But let me end by explaining that there is worse than all this. If you look, following our analysis of nuclear winter, at the fire zone of a 100 kiloton warhead, such as those carried by our nuclear forces, you go to a fire zone of about 86.5 square kilometers. So 1,500 kiloton warheads, that's about 1.5 megatons, is 1,300 square kilometers fire zone. And a 1,300 square kilometer fire zone can generate as much as 5 teragrams of soot, depending on the combustible material loading of the targets. This surpasses the nuclear winter threshold that we mentioned earlier in the India-Pakistan regional war scenario. Now, if we look at a fire zone generated by 40 100 kiloton warheads, which could be carried by one of our SSBNs, that's a 3,464 square kilometer fire zone. That can generate between 10 and 15 teragrams of soot. But who are we deterring with this? Well, the combusting loading of Chinese cities is similar to India and Pakistan. So the estimates made for those are fairly valid in the climate modeling. The combustion loading of Russian cities is about 60% of India and Pakistan. Thus, even in a best case scenario, one Vanguard SSBN can generate between 6 to 9 teragrams of soot, well above the nuclear winter threshold. So the catastrophic effects that I've been talking about are genuinely a real and present danger all the time we rely on nuclear deterrence. And I leave you with the thoughts of our great hero here, who set Pugwash in motion by signing the Russell-Einstein Manifesto, that every thoughtful, well-meaning, and conscientious human being should assume in times of peace the solemn and unconditional obligation not to participate in any war for any reason or to lend support of any kind, whether direct or indirect. Okay, thank you for your attention today.
Wonderful, David. Thank you so much for that excellent presentation, which was very enjoyable. I'm just going to put into the chat the link to British Pugwash membership and the link to our YouTube channel, because there was lots of very useful facts and stats in that presentation. And so you can check out David's presentation again on our YouTube channel, which I'm just about to put into the chat. But yeah, if anyone would like to ask David a question, we've got a bit of time now for a Q&A. So you can either raise your hand using the chat, the react function, you'll see at the bottom of the screen, or you can post a question in chat. So yes, would anyone like to ask David a question? Otherwise, I will get the ball rolling. Maybe while people are having a think about it, David, my question was about the recent announcement by the United Nations that they're going to create a panel tasked with examining the physical effects and social consequences of nuclear war on a local, regional, planetary scale. But that was actually voted against at the UN by the UK, and the UK has justified this by saying that there's clearly established knowledge on this, it won't change collective understanding, there's abundant scientific research, and it won't produce new info, therefore it can't won't be advanced by this study, and the terms of reference are very well framed. So I was just wondering what your thoughts were on that and what you think the benefits are of the UN conducting this study.
Well, I mean, I think all these studies are very important. I mean, the work that I've talked about today, done by climate scientists, is not funded. So it's some funding has now been got by the leaders in this in Rutgers, but it's something that as scientists we have to be very cautious because we do not like to be put on the stand about policy. So science, like I said, it's not about authority. It's not about telling people what to do. It's just about helping people frame a problem and find different avenues of understanding. And the way science works is a system of cooperation. So I think it's important that the UN conduct these studies. Um, I think, as in climate modeling, I think you need to run many different models. So one of the big problems with climate change is that as we've actually increased computer power, the models disagree more. So when you see the predictions from the uh, from the United Nations about climate change, they are averages of many different models, which sometimes disagree about very important effects and past events. And these are really challenging scientific problems, but that's why you do these kind of back of the envelope calculations to convince yourself that you're going in the right direction, and then work with the models to try to understand more about the processes involved. So, but all of this, I think, and the reason I tried to break it down into a few simple numbers is that all of this is incidental because it's kind of obvious just how serious and awful this situation is and how terribly dangerous nuclear weapons are. Um, and so I think it's important that we collectively fund and organize these studies on an international scale. But I think it's up to all of us as individuals to take an interest in this and try to grasp it in our own way. Because, we're living in unprecedented times. So I don't know much about the politics, but I'm very concerned that science is under attack in the way it is at the moment.
Absolutely. Okay, thanks for that. Tony Staunton, would you like to ask your question if you'd like to
Yes,
answer?
thank you. I mean, I'm vice chair of the campaign for nuclear disarmament in Britain. So, David, that was superb and really helpful and very interesting. And obviously, I'm more a social scientist than, than a mathematician or a scientist, but it's helpful to be able to identify what I think we all know in aspect. And one of the things about that is that the general consensus is that, oh, well, if there's ever a nuclear war, that's it, we're all finished. And there's almost a nihilistic element of that, which is just, well, we're all going to die sometime, so if we all go together, so what? And we have to keep reminding anyone who comes up with that blasé phrase that actually the majority of people don't die instantly. And it can be a protracted period of time and the most horrific pain and suffering in the process. But that doesn't necessarily put people off supporting nuclear weapons. I live in Plymouth, in the southwest of England, and we have the nuclear dockyard that services the Vanguard submarines, and it produces jobs, creates jobs, some of them quite well paid, and the population is very supportive of that nuclear dockyard in general. My big concern about your whole presentation and our argument, because we argue the same as you, David, is that there is an enormous amount of political evidence that the people who are currently running things in various countries believe that they can get away with using one or two nuclear warheads. Because, rather like Hiroshima and Nagasaki, well, we use them and that scared everybody off, and everybody's done what they're told ever since. Of course, there was nobody else with nuclear weapons at that point, so the argument doesn't stand up. But Trump has talked in such terms, and of course, so has Putin. But the India-Pakistan conflict in the last fortnight actually raised this issue very, very starkly of the potential for one warhead to be let off. And I wondered what you thought about that in terms of a potentiality, and of course, how we get to these leaders to explain to them that this is not the case.
Thanks, Tony.
Well, I really am just a theoretical physicist, so I don't have answers to the big problems. But I do think that it's incumbent upon us all to try to understand the situation, to talk about it intelligently, and to bring it back more into public discourse. And it's very worrying that as the Doomsday Clock ticks closer to midnight than it's ever been in its history, at any point in the Cold War, we're closer to midnight now, that this is so far off the radar of the general public. And politicians aren't going to pay attention to anything that's off the radar of the general public. So the first thing to do is to get this back into the public consciousness in a very robust way, and I think that begins with schools. So climate science is something that has really made great strides in public understanding over the last 20 years, and despite the enormous challenges that we still face, many people understand that there are real effects from taking a lot of carbon that's buried underground and putting it up into the atmosphere in massive quantities. Even though, as I said, the problem of modeling this is a very big mathematical one. So I think we have to, if you want politicians to pay more attention, it's up to us to spread the message so it becomes something that they have to pay attention to, because it's something the public cares more about. And so as Pugwash has joined with the Physicists Coalition for Nuclear Threat Reduction. So my colleague at British Pugwash, Peter Collicott, and I have been going into UK universities to give talks and to try to get this even into the mind of young physicists. So I think we all have a small radius of people that we can talk to and share with, and share our concerns. And I think it spreads from there, and you just have to keep paying attention. But I don't know how to address politics in any more direct way.
Great, thanks, David. I'm going to take two questions together then. Alan, I see you've got your hand raised, so I will come to you in a minute. And then we'll probably wrap up soon after that. So there are two questions. One from Elford Jones. It says, was the asteroid that you mentioned in your talk ever in danger of shifting the Earth's axis? And then Sarah McKee asks, thanks for your talk. Currently, there are a bunch of programs to modernize warheads to keep them, quotes, safe and reliable. These efforts allow the use of only one warhead to be used on hardened targets versus the use of multiple warheads in the past. So the stockpiles are reducing in number, which you think would imply disarmament, but becoming far more lethal. This then makes the risk of miscalculation and escalation greater. Add to this the integration of AI, and it becomes very unpredictable. How do we make the point to policymakers that modernization efforts and the development of non-nuclear supporting technologies are escalating the problem exponentially?
Okay, so I take the easy one first. No, even with an asteroid like Chicxulub, it really was. I gave the picture of like a mosquito hitting your window screen as you go down the highway. It makes a big mess in the atmosphere, but it was very a fraction of a percent of the momentum of the Earth going around the sun. So the Earth hardly noticed it as a whole, but it certainly created an enormous mess on to our planet and its ecosystems. To do with modern developments, I'm not the most qualified person to talk about that. Like I said, nuclear war planners are mainly concerned with blast effects. So sometimes they want to have a stronger yield weapon penetrate deeply at a target, and rather than spread out the blast effects, as I indicated, which also spreads out the fire zone. There's so many uncertainties in this. You know, it's like playing Russian roulette. I mean, just put down the gun. It's just absolutely ridiculous to have these type of conversations and try to become competitive in the idea of nuclear war. We all just need to work together to get rid of these weapons, which were a big mistake. Like I said, science doesn't tell you what to do, and so when we invented nuclear weapons, or the possibility of making nuclear weapons, it was a big mistake that the human race went forward with that. And I gave a talk last year to the Bertrand Russell Society AGM, where I talked about the same big mistake that's going on right now with AI. So if we don't take really proactive measures to limit the development of AI, we're going to have a very big problem on our hands in the near future, because it's an authoritarian system. At the moment, we're very wowed by generative AI, but as agentic AI comes along, that's AI which will have real agency, independent of us. It won't just be answering our questions. It will be taking agency and telling us what to do. That's on the horizon. It's a real and present danger, and I'm afraid we're not doing anything to stop it. So we need to put limits on the training, the energy consumption of the training of these models right now, so that we can't train larger models and develop those type of capabilities, at least in the near future. So I think science gives us these possibilities, but it doesn't tell us what to do with them, and that's when politics and the good wisdom of the average person has to come in and say, no, this we don't need this.
Great, thank you very much. Okay, Alan, so I think this will be the last question, unless anyone has any burning things they want to ask, and then we'll wrap up. So yeah, Alan, go ahead.
Thank you very much, Tim, and I apologize for the black screen. I'm not hiding, it's just the camera's just broken for a minute. So I'm Global Coordinator of Parliamentarians for Nuclear Non-Proliferation and Disarmament, and also the Program Officer for the World Federalist Movement Institute for Global Policy. I have a very quick comment, then a question, and the comment is, David, thank you for a fantastic presentation. I do want to push you a little bit, though, out of your comfort zone, because you first mentioned that you wanted to stick to theoretical physics and the facts, physical science. That's where your expertise is. But I encourage you to follow the model of Bertrand Russell and Albert Einstein, which they broke out of their particular specialities to really look at the implications of these issues for politics, even if they might not be political scientists. And the ideas coming from physical scientists or social scientists for political scientists are really important, because the political scientists haven't yet got all the answers. So asking the questions and coming up with new ways of seeing things through intersectionality of science, I think, is really, really important. And to me, that's what Pugwash was demonstrating by bringing, thinking minds together, in the Thinkers Lodge, which is what it's called, to sort of break out of the categories we might put ourselves in. And then at the end of in one of your answers, you actually started doing that and started talking about, ideas of cooperation, which I thought were really good. So then my question is, we're in this mess at the moment through primarily, not only nationalism. Nuclear weapons are there to deter nation states. There are other reasons, of course, power, money, but the primary role for deterrence is that. Einstein took that head on and said, we need a supranational authority, a world federation, for example. That may not be possible at the moment, but it's out there as sort of a thought. But what could be possible is to look at what are the security roles for nuclear weapons, deterring aggression, preventing someone else from using nuclear weapons against you, and finding efficient, effective alternatives to that. Now, you mentioned one of those alternatives that you put up is diplomacy, but that's only one. There is also common security, international law, the International Court of Justice, international arbitration, the better use of mediation. There are a whole range of common security tools that could replace nuclear deterrence. So my question is, how can we elevate these? How can we help people understand that there are effective tools to resolve conflicts, international conflicts, and achieve security without having to rely on this threat of annihilation? Thank you.
Okay, thank you for all these hard questions. Um, Referring to Albert Einstein, yes, he was a peace activist for a great portion of his life, and he dedicated a lot of time to this. But you know, to Einstein, it was actually quite clear what needed to be done, and you've outlined that there. He felt that like a supranational authority must be resorted to in times of aggression and potential war and conflict. And we must cede some of our sovereignty to such an organization if we are to end war. And I think one of the most powerful statements that Einstein and Russell made on this, actually, it was Russell that wrote this. He said that we must understand now that we've entered an age where we understand that science and war are no longer mutually compatible. So we must either give up progress in science or give up war. But if we try to keep both, it's going to end in disaster. So, I mean, how do we advance that agenda? I think things change very slowly, and we have to have a generational view of what needs to be done. And again, I resort back to education. We must continue to educate the next generation to understand that ultimately the rule of law, as you suggested, the rule of international law, is the right way to arbitrate. And this idea of it's been more than 130, 40 years old. And we have to keep working towards that, and have hope in the future. These are very big problems, and we mustn't be overwhelmed by it. We just got to keep doing whatever we can in our small field of expertise and influence.
Great, thank you, David. Some people have put some useful links in the chat, including Alan's, a link explaining the idea of common security, other people, some events which are worth checking out. Paul Rogers is doing an event soon. But to finish, yep, I think I see a hand from Yue So. So would you like to ask a question, and we'll wrap up after that? Go ahead.
Hi, yes, I'll ask a quick question. So I'm an undergraduate physics student at Imperial. My question to you is, as a physicist, how can we get young physicists like me to be more engaged in nuclear disarmament, given that the great problems of this world now, as what the younger generation sees, is things like AI and climate change, rather than nuclear disarmament? Thank you.
You're welcome. As a physicist, I've always taken interest in the physics. And so, rather than, it's important just to play around and develop your intuition. And this is why I always advocate, doing these little calculations, back of the envelope calculations, to get a feeling for the order of magnitude of different phenomena. So that's something that really helps you as a physicist, but it also brings into your consciousness the dangers of different technologies, and in this case, nuclear weapons. So, what I think is amongst your physicist peers, you share an interest in the physics, and that's somewhere to begin because it's a shared interest, and you can talk about the dangers of these weapons and find an interest in how they were developed, but then keep your kind of consciousness at a level where you appreciate the danger of these things. And instead of turning it into an experiment, turn it into a position of advocacy and to eliminate this terrible mistake that we made in the past. And it's very close to getting out of control now because there are great proliferation risks for nuclear weapons in the near future, in the coming decades. And we need to get a cap on this sooner rather than later. So please just start by sharing the physics with your colleagues, share your common interest, and then build on that. Okay, thank you so much.
Well, thank you, David. And on behalf of everyone here, I'm sure we're extremely grateful for your talk today, which is really useful. It will be shared, as I say, on the British Pugwash website. Please check out the website for updates, for future events, and to consider joining. So, yeah, thanks for joining today. Once again, thank you, David, and see you soon for a future event with British Pugwash. Thanks, everyone. Take care. Have a good evening. Bye-bye. Bye.
Thank you.